And so now it's my pleasure to introduce two people that I have known for a very long time. And I'll introduce first Andrew Fraknoi. He will be our interviewer of Frank Drake. Andy is the chair of the astronomy department at Foothill College, but that's sort of his sideline almost from being an astronomy star in the Bay Area. You hear Andy on the radio, you read articles in the newspapers where he's been interviewed about what's happening astronomically. Occasionally he gets to make a comment on astrology, which is one of his favorite topics to beat up a little bit, and that's great. He teaches courses on astronomy and physics for poets to about 1,000 students each year. So he's bringing astronomy and space sciences to the people that are phobic about math in creative and generous ways. In 2007, he was selected as the Professor of the Year by the Carnegie Endowment for Foundation, the Professor of the Year for the entire state of California. This was really quite an honor. Andy has worked with the Astronomical Society of the Pacific for years and years, and I expect that he penned the article that was handed out to you about Frank Drake. You didn't pen that one? I didn't read the back of it. Frank penned it. Okay, that even better. Autobiographical. Andy's a textbook author. He and Dave Morrison and Sidney Wolfe took over the classic Abel book and transformed it into astronomy textbooks for succeeding generations of students and worked together for quite some time. Asteroid 4859 has been named for Andy. It's called Asteroid Fraknoi. They're much more formal. By the International Astronomical Union. And currently, Andy is the vice president of the board of trustees for the SETI Institute, for which we're very grateful. Frank Drake is the pioneer SETI researcher in modern times when technology became capable of starting to search for technological civilizations. Frank first did an experiment in 1960 to see if he could find a signal from an extraterrestrial source. And maybe he'll talk a little bit about that. I don't want to take away any of your thunder. He participates in ongoing research, developed optical SETI with the University of California at Santa Cruz and his colleagues at Lick Observatory, and used the 40-inch nickel telescope for some time to look for optical signals, which was another way of seeking evidence of extraterrestrials. He's interested in the possibility that very numerous red dwarf stars, those stars that are much less bright than our sun and much more prevalent, might host stars. But there's much more to talk about, and I'd like to invite Andy and Frank up here for the conversation. Frank is also a member of our board of trustees. And they can go into all the fun details about Frank's career and his life. Thank you.
So welcome, everyone. It's an incredible honor for me to have a conversation with the pioneer of SETI, Frank Drake. I don't think anyone had a conversation like this that was recorded with Galileo. No one got to have one with William Herschel. No one did it with Edwin Hubble, but I get to do it with Frank Drake. So it's a delight to be able to do that.
And I'm delighted to be interviewed by Andy. We've interacted ever since I came to California in 1984. And we've been associated in one way or another in the Astronomical Society of the Pacific. And for those of you who aren't aware, Andy is really one of the foremost teachers, popularizers, and reporters of astronomy in California, and particularly the Bay Area. Yes.
Well, thank you, but that's the last we want to talk about me, and we want to go on to talk about you. So we've agreed with Frank that we're going to alternate this conversation between Frank's current work, which I think you'll be very excited to hear about, and some of the classic things that Frank has done for SETI. So I'm going to begin with the very beginning. Tell us a little bit, Frank, about how you got interested in astronomy. What brought you to this field?
I got interested in astronomy at about the age of 8, when one day my father told me that there were other worlds in space. And to an 8-year-old kid, that sounded like a world exactly like the one I was living in, which was the south side of Chicago. And I was fascinated. I wondered, do they have cars and streets and all the same things I had? And of course, that was a foolish idea now in retrospect. But nevertheless, I was fascinated, and I can continued to have that fascination the rest of my life. It was always in my mind, are they out there? How could we find out? And finally an opportunity came much later, stimulated by when I was doing my graduate work at Harvard and was a lone graduate student working in the cold dark of night at the Harvard Observatory. Even on rainy, stormy nights, because radio telescopes, unfortunately or fortunately, work day and night, and even when it's raining. And one night I was observing the Pleiades star cluster and measuring the spectral line of hydrogen that was then very popular in astronomy, still is. And I'd watched it for many nights, observed it over and over. It had a double-peaked spectrum because of hydrogen in the Pleiades star cluster itself. And then one night there was a whole new feature there. A sharp spectral line had joined the two features that were due to hydrogen gas. And I took that feature and calculated its frequency and determined what Doppler velocity was associated with it if it was in fact coming from the Pleiades star cluster. And it turned out to have exactly the known velocity of the cluster. And I thought, wow, could this be creatures on the Pleiades sending signals and sending them at the rest frequency of the hydrogen atom? And it turned out this was actually coming from a nearby radio amateur transmission, as I found out a few nights later. But it made me do the calculations and see what could we detect. And at that time, we were on the verge of having the sensitivity of detecting the strongest signals we were then radiating from Earth from the distances of the nearest stars. And just a few years later, when I was at Green Bank and had a bigger telescope and a much more sensitive radio receiver, then the equations showed we could detect transmissions just like our own from the distance of the nearest stars. And that led to the search in 1960 for signals from the stars Tau Ceti and Epsilon Eridani, which was made with, the searches were made with a one-channel receiver. Today we have receivers with 100 million channels, and bandwidths, in that case, of about 100 hertz. Today we use 1 hertz, which makes the search much more sensitive. Didn't see anything, but it was a start. And it did stimulate a lot of other people to start searching because they too recognized, yes, indeed, we could detect civilizations like our own from nearby in the galaxy.
So when, this is something that has been in different ways in the literature, when the Morrison and Cocconi paper came out, you had already been thinking about doing the search independently, is that right?
We had started building the equipment in 1958, quietly, for several reasons. One is we knew that it would get a lot of popular attention and we didn't need that. The other was that we were a taxpayer-supported observatory, and there was a fear that we would be criticized for using taxpayer monies to do a search which is so highly speculative, maybe even in some people's minds kooky. So we kept it quiet, and we were in fact about ready to start observing. We'd actually been building the equipment for 2 years in 1960 when the Morrison and Cocconi paper came out. And what happened then, which was very interesting, was that the director of the observatory at the time was the very great astrophysicist, one of the greatest of the 20th century, Otto Struve, who was the director there, and he was very encouraging, and he believed very strongly that there was intelligent life in space and wanted it to be found. But he was also very conscious of credit and priority. And when the Morrison and Cocconi paper came out, he sort of freaked out as to how to describe it, because we had not said anything publicly about what we were doing. And so he made it a point to go around the country giving lectures, announcing that, hey, those guys weren't first. Yeah, and that's the history.
Excellent. So now many of you know that Frank has written a book called Is Anyone Out There with Deva Sobel, who, after she wrote the book with Frank, went on to great heights of science writing. And a few years ago, Frank allowed us to reprint, and he actually revised the story of how he came up with the Drake equation. And I think everyone has a copy of that handout. So we're not going to go into that in great detail, but I'm going to ask Frank instead what your view is of the Drake equation today. How do you see the numbers, and are you optimistic, more optimistic or less optimistic than you were when you came up with the equation in the first place?
The equation has existed now for 51 years. And over those 51 years, I've gotten many suggestions for additions to it or improvements. But in my view, and maybe I'm being protective, all of those things can be subsumed into the existing equation. For instance, people have proposed that there ought to be a factor to account for naive politicians, which have, and such people have interfered greatly with the progress of SETI in the United States. They've stopped the NASA SETI project in 1993, and NASA's never gotten back into the SETI business, even though at one time it was a very hot subject in NASA, and rightly so. But the naive politicians have done in our civilization steps which would have slowed the detection of other civilizations. Anyway, all of those things I think can be subsumed in the original 7 factors which are in the equation. What has happened is not a change in the equation, but a great improvement in the numbers that you put in it. It has 7 factors, so it means the accuracy of its result, which is a prediction of the number of detectable civilizations in the galaxy, the accuracy is dependent on the factor which is least well known. And unfortunately, that one, which is the longevity of civilizations in a detectable state, is still unknown and will be till we detect other civilizations. So we have that problem that we still have one factor with a large error bar on it. But some of the others are really very well known, which they weren't 51 years ago. The only one that was known 51 years ago was the rate of star formation. And that one has been improved somewhat, but it hasn't changed greatly over 51 years. One of the key ones was what fraction of stars have planets. And there, of course, you all know of the great breakthrough, the monumental discoveries of the last 10 years, which I think history will look back upon as one of the greatest advances in the history of astronomy and science in general, the 3,000 planets or something we know of. The result, a very important result, that something like more than 1 planet per star on average in our galaxy has come out of those observations, which, by the way, affects the planning for our searches, because what it says is that you really don't know enough to sort out which stars you should look at for planets and intelligent signals, because every star is a good candidate at the present time. Every star, because we don't know enough. The Kepler project can only detect fairly large planets. It can best detect planets that are in close to their star. It misses most of the planets that are out in the so-called habitable zone where the Earth is. And that's something to keep in mind, by the way. We saw yesterday the diagram which showed all those detected planets. But remember, the Kepler approach depends on the system being aligned so that we get eclipses at Earth. And the probability of that is easily calculated. And what it means is that we only detect about 1 in 100 or 1 in 1,000 of the planetary systems through the Kepler approach. So there are all those planetary systems, but that's a tiny tip of the iceberg. It means there's probably 1,000 times as many out there as we are detecting. So that has improved our values for some of the factors in the equation. We've also detected planets that are perhaps habitable in the in orbit around M stars, and that's more than 80% of the stars of the galaxy, which means the potential life-bearing planets has increased very greatly in number. So we not only know the numbers better, but the real answer is that the results have made us more optimistic. All the results so far have been positive in the sense of suggesting that the abundance of life is of intelligent life is much greater than we thought 51 years ago. The one unknown parameter, as I mentioned, was the longevity of civilizations. On the negative side, there is one thing going on which I think about a lot, and that is based on the fact that in thinking of our searches and what's detectable, we have to use ourselves as a model. We don't have any other civilization to use as a model. And in our model, our civilization over the last 50 years has become very detectable, primarily through our radio, television, and military radar broadcasts. But in recent years, the detectability of the Earth has started to decline. Not because our civilization is going downhill, it's because we're getting smarter and more technical savvy, and we can use television transmitters and radar systems which have much weaker transmitters and still do the job. And just to give you a number, because numbers matter in this business, we quantify things in SETI, we're not just playing around. The old-fashioned analog TV transmissions, which we lived with until a few years ago, typically had transmitters of 1 million watts, radiating out most of the energy going into space. On the Sutro Tower in San Francisco, that tower radiates about 31 million watts. Now, the wave of the future is direct-to-home broadcasting of television from satellites. The transmitters on those, which it's hard, most people don't know about, are typically 20 watts, not 1 million watts, 20 watts. And the radiation is beamed very carefully onto the surface of the Earth. That's where the television sets are. The amount actually escaping into space is a watt or two. That's all. So 1 million watts is fast becoming 1 watt. And 100 years from now, I suspect we will not have any more 1 megawatt transmitters. We'll have lots of 1 watt transmitters. But the Earth may become almost undetectable. And of course, that's a depressing idea. But it's reality, particularly if our civilization is typical. And I think it will be, because the march of technology which has brought this about, which mainly involves creating a presence in space, will occur in all civilizations. So there's a lot of upside, there's some downside, but there's some answers to how we might not only stay detectable, but also how we might be able to do a much better job of detecting.
So I've got a couple of follow-ups to those thoughts. First thing is, what's N? What's the number? Of course, you're not going to give us the definitive answer, but what's your thinking these days about the number of intelligent technological civilizations that might be out there?
Well, if you take the consensus of astronomers and biologists about what the factors are in the equation, the first 6 factors have and still multiply together to about the value of 1 per year. Okay. That's, by the way, an interesting number. It says there's 1 new technical civilization in our galaxy a year, which is a pretty heady result. It means there have been lots and lots of them, and a lot of them are still out there. Which says that really the whole thing is, the number is just 1 times whatever the longevity is. And the longevity is the thing we don't really know. When we use ourselves as an example, the longevity has been perhaps 100 years. Now that's depending on our detecting our powerful radio transmissions. If you have a way of detecting very faint light signals, we've been detectable longer because people could detect the lights of our cities at night. And I'll tell you in a minute, I think, how that's in our future. If the lights of cities at night become detectable, then the longevity may be very much longer than 100 years or so. So there's some interesting aspects of this that have to do with what our future is. But in any case, if you take as a possible longevity, which you can recognize from what I just said, has to be essentially a guess. It's more than 100. But how much more, we don't know. I like the number 10,000. Don't ask me how to justify that, because we don't have any human experience to justify it. But optimism about how our technology will keep us visible, either through radio or light waves, makes me use the number 10,000, in which case n is 10,000. Now that's a good number. Lots of civilizations to detect if you believe it. Now, of course, I've told you how uncertain that number is, but it doesn't make the search easy. 10,000 civilizations out there, and last night when I was talking about Jill, I mentioned those are all the finish lines in the galaxy. There are 10,000 places you could arrive at and find a civilization. But that means only 1 in every 10 million stars has a detectable civilization. So there are lots of them, but it will take a lot of searching. And this is the big challenge to our SETI program, why we need to do much more than we do, why we need much more money, because we need to search literally millions of stars before we'll have a high probability of succeeding. Now, we may luck out, you know, people do win the lottery by buying 2 tickets or so, but, and what we're doing here is really playing the lottery. We're searching, and every time we search, we're buying a ticket in the lottery, but the chances of winning in any given ticket is less than 1 in 10 million. 1 in 10 million, which is what we're dealing with. And you may ask, oh boy, why do you even spend your time on this? And the reason is, and there's a good reason, that we know that the detection of extraterrestrial life will so enrich our civilization in many ways, sociologically, technically, theologically, everything important to us, that it's worth buying all the lottery tickets it will take to win the lottery.
So let's talk about, since we can't rely on winning the lottery every time, let's talk about other ways that the human civilization might do better. I know you've become interested in using visible light rather than radio waves to search for civilizations. Tell us a little bit about that, and then we'll talk about gravity as a way of detecting.
Yeah, okay, good. Well planned.
Good.
Actually,
He coached me.
There's a little conspiracy going on here. Traditionally, of course, SETI has been mostly radio searches, not entirely, but almost always. And in the microwave region, there have been over 100 searches, lots. But we are dealing in this case with trying to detect intelligent creatures, and just what they might do, which is detectable, is not really predictable. Intelligent creatures aren't always logical. They may do something which is detectable that may not seem logical, but nevertheless, it would be there to detect. One thing which came to light a few years ago was the possibility that they would be signaling other civilizations using light flashes of light. Now, there's 2 things about that to keep in mind. If that's happening, they have to be altruistic. They have to be wanting to give benefits to other civilizations with no benefit to themselves. And it raises an interesting question. Is altruism a common trait among intelligent civilizations? Very interesting question. Nothing to do with physics or astronomy, but with the goings-on and thinking and ethics and morals of intelligent creatures in general. I've given a lot of thought to that. I've kind of finally concluded altruism, which humans have a great deal of, is actually perhaps of Darwinian origin. It conveys, in fact, survival value to you, so that in that case it would be ubiquitous in the galaxy, in which case it would make sense that they would try to help the newcomer civilizations such as our own. Well, how do they do that? Well, they can send radio signals. We're searching for that. But another way which creates signals which are much easier to detect with much less expensive equipment is to send light flashes. And with light flashes, you can send a binary code. You can send messages. Well, why light flashes? It's because here on Earth, again using ourselves as a model, we have developed very powerful lasers that make very brief pulses of light that last about a billionth of a second and radiate a power which is almost unthinkable. While the laser is pulsing, it transmits a power of 1,000 trillion watts, 10 to the 15th power watts. These have been built in conjunction with attempts to achieve controlled nuclear fusion as a source of clean energy. And there are 160 of these lasers at the Lawrence Livermore laboratory, about to zap a pellet about the size of a BB full of helium and hopefully create more energy than is in those laser pulses. Well, these lasers, not intended for signaling, however, are a beautiful source of signals. If you take these lasers and focus the radiation from them into a narrow beam using a 10-meter telescope, such as we have on Mauna Kea, it creates a flash of light which is brighter than all the light of a star by about 1,000 times. And that's all the light of the star on all wavelengths. You don't even need to know the wavelength, which is one of the beauties of it, and gets around one of our big problems in radio, where we try to guess what frequency channel the signal may be on. So in principle, civilizations could be sending signals that are detectable for hundreds of light years with one of these lasers. And it turns out to detect that takes not very much. In fact, if our eyes were sensitive to light pulses that lasted a billionth of a second, we could all be SETI researchers. You go out and sit on a chair in your front lawn in the summer night, look up at the sky, and you would see red flashes in the sky with your eyes, because the flashes are so bright that your eyes can detect them. Unfortunately, we don't have nanosecond time resolution, so maybe other creatures do, but we don't. So that doesn't quite work. Instead, we have to use real telescopes and photomultiplier tubes with nanosecond time resolutions. And that's what we do at Lick and at Leuschner Observatory at UC Berkeley, and at Harvard there's a large project. We look for the flashes, and the equipment to do that costs only a few $1,000s. At Lick we use a 40-inch telescope, an old telescope, but that is plenty big enough to see these flashes from very distant stars. And so far we've looked at over 5,000 stars. We haven't seen a flash. Maybe we haven't looked long enough. And there is a downside to this whole approach, and that is it only works if they are intentionally trying to signal you, because those signals are so narrowly beamed, they have to be pointed at our system or we'll never see them. So it's cheap, and that's why we can do it. It's not very costly. It's easy to do, but it has the downside that we depend on them being altruistic and helping us. Our latest attempt at doing this is to extend our wavelength coverage into the infrared, because the infrared is not obscured by the galactic clouds, and the extraterrestrials will know this and may prefer to send their signals on infrared wavelengths. So we're going into the infrared now. Yeah.
That's great. And now I want to move you on to an even more exotic method that you've pioneered, which is using ideas from Einstein's general theory of relativity about how gravity can act like a lens to help us search for signals from other civilizations. Tell us about that.
Well, as I just pointed out a few minutes ago, it's troubling that intelligent civilizations may be very intelligent for literally millions of years and yet only be detectable for a short time because their technology is so good. Isn't that ironic, that because they're so smart we can't find them? So what we would like is a technology, a detector system, which can detect signals that will always be there. And the prime example is that it's just the lights of cities at night. Also in the radio, even these 1-watt signals from TV satellites and such. Now, if you calculate the size of a telescope, ordinary telescope you need to detect the lights of cities at night, or 1-watt radio transmitters, it turns out in the optical you need a telescope that's about 5 kilometers in diameter. And maybe that is constructible, but it's certainly not by us at the present time. Same story with the radio. You need a telescope that's many kilometers in equivalent diameters, collecting size. So huge instruments far beyond our capabilities, both technically and financially. Has nature provided something that will solve this problem for us? And indeed it has. And I think it is a solution which is really, truly glorious and which is widely practiced in the galaxy by civilizations just slightly more advanced than us because it's so powerful. And it's based on an effect of general relativity, first pointed out by Einstein in the year 1912, which is that a large mass in space bends space. It acts like a lens, although it's not. It doesn't refract anything in the normal sense. It actually bends space so that anything traveling in space does not, after all, travel in a straight line, but on a curved line. And what this means is that light rays passing a star, like our sun, are bent as they pass the star and eventually are brought to a focus. And this was observed for the first time in the year 1919 during a solar eclipse when the images of stars looked at along paths passing close to the eclipsed sun, it had to be done in an eclipse, were found to be bent. The stars changed their position in the sky. It was a tiny amount, but it was exactly as predicted by Einstein's theory of general relativity. Well, this means that every civilization has one grand lens called its star. We call ours the sun. And my thought is that every very advanced spacefaring civilization will exploit this lens that is given to them. They'll all have it. They all have this potential. And will use it to build, in effect, a giant telescope that can detect incredibly faint transmissions. Now, how faint are these? The gravitational lens of our sun, of course, turns out to be bigger than the sun. The rays pass by the edge of the sun and are brought to a focal point. The rays that are very close to the sun, closer than the radius of the sun, of course, don't come to us because they run into the sun and are absorbed. But there is, in fact, a ring of light, if you will, around the sun. And the light from that ring is focused to a focal point. And what you have is, in effect, a lens of very large diameter, more than 1 million miles in diameter, with a collecting area which is of the order of, the way most easily to understand, typically of the order of 100,000 Arecibo radio telescopes. That's how much the collecting area is. So the image is very, very bright and very, very sharp. Well, that's all good. The problem is the focal point where this image is created is about 500 astronomical units from the center of the sun, which is about 10 times the distance to Pluto. We don't have any spacecraft out there. To use the gravitational lens, you have to get at least 500 astronomical units from your star. And actually, you need to go farther than that because the rays that graze the sun, which are focused to that point, are going to be distorted by the gases in the solar atmosphere. So you need to get out probably 600 or 700 AUs before you'll get sharp images from your lens. With our present spacecraft, it takes about 40 years to get there. And that's why nobody's doing this, although the Europeans are now planning a mission to the focal point to see if, in fact, all this works. Now, we know it works, by the way, because we have seen galaxies acting as gravitational lenses, focusing the images of distant quasars. This is now well established. The whole thing does work. And in fact, we have seen now there have been a way of detecting planets by stars creating images of planets that happen to pass behind them. And this is one of the new ways to detect other planetary systems. So we know it works. So we know when we get out to 700 AUs or so with a fairly modest thing. It doesn't take a big detector, just a 10-meter antenna work just well, very well, we will have a gravitational lens telescope. And if you work out the sensitivities, it easily detects ordinary television broadcasts from distances of hundreds of light years. In the optical, it can detect the presence of planets and the lights of cities at night. And the resolution is so great that you can actually resolve the planets and see that there are cities and such. You actually will see in detail what the planets look like by the lights of their cities. And this is so powerful that I think that all planets do it, all intelligence-bearing planets do it. And this is how advanced civilizations learn really in detail about the life around them. Now, this is probably 100 years in our future, unfortunately. So live a good, clean life, and maybe you will see the first results of gravitational lenses. But it's not going to happen tomorrow. But it is possible. The fact that the phenomenon works has been proven. And it doesn't take a terribly exotic technology. We can build spacecraft and propulsion systems that will get out to the required distance. We're not yet doing it.
So that's very exciting. There are a variety of ways that we might in the future get to know that there are civilizations out there. And I want to now take us to the response question. So supposing we do discover a signal or an incontrovertible proof that there are civilizations out there, we manage somehow to identify where they are and even the channel or frequency on which they like to communicate. Now we get to the question of actually sending messages. You sent a message to a globular cluster some years ago. Since then, there have been voices that have urged us to hide from evil, slobbering aliens out there and not responded anyway. And I wondered what your thought was about eventually responding to whatever message we might discover.
Okay, well, I'm all for responding. But the question is, what should be the response? And that's often the way the question's asked. What would you say to an extraterrestrial? And the answer is, it depends. It depends on what they are. I think that the first signal we will detect, by the way, I'm going to throw out a prediction just so you'll remember it. I think the first intelligent civilization we will detect will be from a star that isn't in any catalog. I think it's at some great distance, hidden in the dusty cloud. M star, perhaps, not in anybody's catalog. Anyway, that's an aside. I think the first thing we will detect is likely to be a radar transmission, which consists of a series of pulses. It will tell us there is indeed a technology in space of intelligent origin, but it will tell us nothing about the technology. And I don't think you can send a meaningful response till you know something about them. So I think the scenario I have is that we will detect a signal with just enough signal and noise to know there is a technology there, but not with enough signal and noise to learn what that civilization is like. What kind of creatures are they? Are they fish or amphibians or primates like us? What are they? And so I think the next step is not to send anything, but rather to build whatever instrument it will take to learn about the civilization. That may take years, of course, but learn about them. And after you learn something, then make some wise decision about what would be wise to send them, if anything.
And some people have speculated that the very first civilization we might find would be one that consists of artificial intelligence, that civilizations might evolve into machines or some kind of form which is no longer organic. Is that at all a thought that you like to pursue, or is that science fiction?
Yes, no, that's not science fiction. It's very possible that the first signals we will get will be from some robotic source. And of course, that will give us guidance as to what would make sense to send back. Is maybe the signal's asking for what frequency we prefer to send on. But I think the idea that signals may come primarily from robotic sources or often is perfectly sensible.
I want to ask you a last question because I know we have to go to our next session. But one of the most exciting things I think that you did with Carl Sagan was to put the sights and sounds of humanity on a golden record and send it out into space. Well, what are your thoughts now about that golden record, about the Voyager message that we've sent out? Many people talked about that being really a message to ourselves, that we need to last long enough to, in a sense, wait for it to arrive. What are your current thoughts about the messages that you've sent?
Well, the Voyager record and its predecessor, the Pioneer plaque, were messages both to the aliens or the extraterrestrials and to us. To us, it was a demonstration that one can send meaningful messages from one world to another. So that it's not a crazy idea to think that we might receive messages, in this case in the form of artifacts from other worlds. So it showed interstellar communication was possible. That was the message to us. The message to the aliens was that once upon a time on the planet Earth there was a civilization, and on the Voyager record there are 112 pictures of our civilization, of our people, of everything about our civilization. And so if they capture it someday, and it will be a long time from now, it takes millions of years just to go to the distance to the nearest star, they will learn about Earth from this record. And another thing which always gives me goose pimples is that, in fact, the golden records on the two Voyagers are encased in a nice metallic protective case. They will survive in space, undamaged by the erosion of dust particles and such, for literally many billions of years. They will exist till long after the sun has expanded and swallowed up the Earth, and we have all moved on or done something, or maybe disappeared. But 10 billion years from now, there will still be a record of the existence of our civilization out there for anyone who happens to find it.
That's great. Well, I've mentioned this before at other SETI events. A few years ago, I started just doodling a little equation about the chances of finding another Frank Drake out there. You put together the chances of there being a scientist pushed in this direction by an interesting signal, someone who's willing to stand up to the scrutiny and the ridicule of undertaking such a project, someone with the right technical skills to do this kind of work, someone with the inspiration to put together a program like the Drake equation. And when I factored all those factors in, it was remarkable. Every time I did it, N turned out to be 1. Frank Drake is unique. Let's applaud and celebrate him, ladies and gentlemen. All right, enjoy the rest of the conference.